Okay. Yeah. Hi. Thanks everyone for coming. Today I'm going to be talking about a joint work with Ian Wanless at Monash University. Not as closely related to graph theory as most things I do, but there will be graphs at the end of the talk if you stick around. Okay, so I'll start off just by explaining some of the words in this title. So covering radius in the Hamming permutation space. So firstly, permutations. So you can think of a permutation as just a string of numbers, string of the numbers from 1 to n, where each number appears exactly once. Or you could think of them as, functions whose domain and image is the set of numbers from 1 to n. I'll usually think of them as strings, just because they're easier to write this way, and it won't really matter for our purpose. Okay, so the Hamming distance between two permutations just counts the number of positions in which the two permutations are different. So here, if you look at the permutations 1, 2, 4, 5, 3 and 1, 5, 4, 3, 2, there's 2 places where they're the same, so there's 3 places where they're different, and the Hamming distance there is 3. Okay, and finally, the covering radius. This is just asking the question, if we want to cover a metric space with balls at a given set of points, how big does the radius of the balls need to be? This is the covering radius of a set of points. So in our setting, so the covering radius of a set of permutations, given the Hamming metric, is just the maximum Hamming distance from an arbitrary permutation to the closest permutation from within the set that we're considering. Okay, so I'll give a bit of an example. So Aladdin's square is just a square array of symbols where every symbol appears exactly once in every row and in every column. So here we have Aladdin square of order 5. And you'll notice that the rows of Aladdin square correspond to permutations. And if you look at it, then what you'll see is that the rows of the Aladdin square form a set of permutations whose covering radius is at most n minus 1. Because if you take an arbitrary permutation, say the permutation 5, 4, 3, 2, 1, then there will be some permutation which matches that permutation in at least one position. In particular, there'll be some permutation from the list which matches in the first position. And this means that the maximum Hamming distance between any permutation and the closest thing from this list is at most n minus 1. Because otherwise it would have to be disjoint from every permutation in this list, and this is impossible. Okay, so this is an example of what the covering radius means for a set of permutations. Actually, we can find a smaller set of permutations which also has a covering radius of at most n minus 1. So, does anyone want to play a game? The game will just involve calling out one permutation and then seeing if this matches up in at least one position. Does anyone want to pick a permutation? Okay, cool. Pick it, yeah. So any permutation of the numbers from 1 to 5, but you want to make it as far away from all of these as possible. So ideally, what you would be looking for is some permutation which doesn't match any of these in any position. 5, 4, 3, 2, 1. Excellent. Okay. So 5, 4, 3, 2, 1. So notice that the third symbol of your permutation was 3. And the third symbol of the top permutation is also 3. So we have a match. So that means that the distance between your permutation and this set is at most 4, and actually is equal to 4. But that wasn't, you didn't do badly, that was the best possible. So yeah, it turns out that this forms a set of permutations of covering radius at most n minus 1, because what you'll find is that whichever permutation you pick, one of the symbols, 1, 2, or 3, has to occur in one of the first 3 positions. because as you go 5, 4, 3, 2, 1, you run out of other symbols to put in the first 3 positions. And then as soon as you put a 1 or a 2 or a 3 in the first 3 positions, it's guaranteed to match something in the subsquare. And in general, we find that there is a subset of the permutations of order n, which uses only roughly half n permutations, and this also has covering radius n minus 1. And this turns out to be best possible. It's not too difficult to prove. It's basically just the Hall's marriage theorem. Okay. So this is the function that I'm telling you to care about for this talk. The function fns asks for the minimum size of a set of permutations which has covering radius at most n minus s. So we were just looking at sets with covering radius n minus 1. So we were looking at basically the value of the function fn1. So just some simple facts about this function. If you want the covering radius of your set of permutations to be 0, then you need to include every single permutation. So this has the same size as the entire set of permutations. But this is also true if you want the covering radius to have size to be at most 1, because actually there are no pair of permutations whose distance is exactly 1. If they differ in one position, they also differ in another position. So these two numbers are just the same. Another simple result, fn0, so we're allowed covering radius to be n. Well, any ball of radius n covers the entire set of permutations. This is the maximum distance between 2 permutations. So we just need one ball. We just need to put one permutation in the set. We don't care which one. And as we just saw, fn1 is equal to the floor of n on 2 plus 1. Okay, so sort of the first interesting case is fn2. And the function fn2 has a relationship between what are called transversals of Latin squares. So a transversal of a Latin square is a permutation which matches each row and consequently a column in exactly one position. So here we have the permutation 4, 3, 2, 1, 5, and you'll notice that it matches every row in exactly one way. The nice thing about a transversal is that the distance between the transversal and the things in this square is exactly n minus 1. It's at exactly distance n minus 1 from each row of the square. However, if we could construct a Latin square which had no transversal, then the rows of that Latin square would have covering radius at most n minus 2. We would find, given any permutation that we considered, we would find some row which matches in 2 positions and therefore had distance only n minus 2 from that permutation. Okay, so some of you might recognize this picture. You can see it at the ground floor of Kézdy. Mutually orthogonal Latin squares first appeared in the literature in 1700, thanks to this Korean mathematician, Choi Suk-jung. Hopefully I'm not butchering that too badly. But 2 Latin squares are mutually orthogonal if the symbols of one square correspond to transversals of the other square. So if you consider, so take this, this symbol here, which I've circled in green. And if you look at all the symbols underneath the top symbol, so that the squares are sort of overlaid here, then we see every single symbol appear exactly once as the bottom symbol underneath this top symbol. And the same happens when you go the other way and you look at one symbol from the other square, you'll find all of the different symbols. But this happens for any symbol that you consider in either square. And these things turn out to be very useful. Particularly, people are interested in finding large sets of mutually orthogonal Latin squares. So the largest number of mutually orthogonal Latin squares that you can have, so that they're pairwise mutually orthogonal, is n minus 1, so the order of the square minus 1. And it's an interesting question to try and figure out when you can find such a collection of mutually orthogonal Latin squares. But this is one of the reasons that, that looking for transversals in Latin squares is of interest. Okay, so what do we know about the function fn2? So it turns out that Latin squares with no transversals do exist for all even orders. So we know that fn2 is at most n if n is even, because we can just take the rows of such a Latin square. It's not too difficult to see that a trivial lower bound on fn2 is fn1. If the so it turns out that fn2 is at least half n. This was improved very marginally to one more than this, so changing this inequality to a strict inequality, essentially. And we have this upper bound of roughly 4/3 n. So this is obviously not tight for even orders, where we have the upper bound of n. But for odd orders, this is basically obtained by taking a Latin square which doesn't have many transversals, and then adding some extra permutations to cover the remaining permutations that are sort of problems. Okay. But yeah, you'll notice that there's quite a big gap between these bounds at the moment. Okay, so I mentioned that there's always even-ordered Latin squares with no transversals, and the proof of that is actually quite simple. But I really like this proof. So we're just going to take the Latin square that you get just from the Cayley table of Z2K. Okay. Okay, it's this square here. So basically, where the ijth entry is just the sum of I and j taken over Z2K. So index the rows and columns by, I wrote the precise thing there, which is why I hoped, okay. Anyway, this is what I mean. So suppose for contradiction that you find a selection of entries which form a transversal. Well, when you add up all of these entries, well, this is the same as adding up I plus j for all of these entries, because every entry is equal to I plus j, where I is the row and j is the column. But also in a transversal, every symbol appears exactly once. So this sum here should just be the sum of all the symbols, all the elements of Z2K. You should use every element of Z2K once in the transversal. But because of this equality, this should also be so this should also represent every row exactly once and every column exactly once. So this sum here should range over the group Z2K twice, because every element is equal to this sum here. However, when for this group Z2K, if you add up all the elements, what you actually get is k. And when you add up 2 times all the elements, what you actually get is 0. And 0 is not equal to k, provided that k is at least 1. Okay. So yeah, this is probably the first Latin square that you would consider if you were looking at even-ordered Latin squares, and it happens that it has no transversals. Okay, so this is sort of the big conjecture for this function fn2. If n is even, the conjecture is that basically even-ordered Latin squares are tight. So this should really be equal to n. If n is odd, then it should be strictly bigger than n. And the motivation for this conjecture was that it would be a strengthening of the following 2 conjectures. which have been open for a long time. So a famous conjecture of Ryser states that every Latin square of odd order actually has a transversal. And a conjecture of this variously attributed to Brualdi, Ryser, and Stein is that every Latin square nearly has a transversal. So what do we mean by a near transversal here? So a partial transversal is just a set of entries from the square such that each symbol appears at most once, each row is represented at most once, and every column is also represented at most once. So if we can find n entries with this property, then we found a transversal. A near transversal is just a partial transversal where you get n minus 1 entries. Partial transversal of order n minus 1. So there's been some progress on this conjecture, some quite recent progress, which I wanted to mention. So every Latin square does have a partial transversal of order n minus log squared n, which is getting quite close, but still a way off. And recently it's been shown that every group-based Latin square, so Latin squares, for example, similar to the one that I generated, but for arbitrary groups. So the group table of any group of odd order. That should say of order. It's not true for even ordered Latin squares still. Okay. So the first thing that we managed to show was something which was actually stronger than this, but this is sort of the simplified version. If the function fn2 is strictly less than fn, then what we know is that fn minus 1, that should say fn minus 1, 2, is at most fn2. And this means that the odd case of the Kézdy-Snevily conjecture implies the even case. Because if we found a contradiction to the even case of the Kézdy-Snevily conjecture, this would mean that we've got some even n where this strict inequality holds, and then this would mean that we don't have the strict inequality for the next, for the lower odd case. The reason this is interesting and not just trivial is that it turns out that this function is not monotone in n, which is a bit surprising. So if you consider just the first, even just the first 4 terms, so fn2 is 2, f32 is 6, because you need to take all of the permutations. But f42 is 4. So this is not a monotone function in n. Although it would be an interesting question to sort of say how badly is this function failing to be monotone. So when can we actually claim something like this? This I think would be interesting to answer, but I don't know if there's much work on this so far. Okay. The main result that I want to talk about today, though, is this new lower bound for the function fn2. Okay, so we didn't get the conjecture, but we did get sort of the first non-trivial lower bound for this function. And our approach was to model these permutations as matchings in a complete bipartite graph. So take the complete bipartite graph with bipartition VW, and you can sort of see that a permutation, for example, this permutation 1, 3, 2, will correspond to a complete matching, so a perfect matching of this complete bipartite graph. So that V1 is joined to W1 because the first symbol is 1, V2 is joined to W3 because the second symbol is 3, and V3 is joined to W2 because the third symbol is 2. And similarly, we can see for the blue permutation, this just corresponds to these 3 straight edges here. So there's a natural correspondence between perfect matchings in a complete bipartite graph, where the vertex sets are ordered like this, and permutations. Okay, so the setup is going to be just that we take a set of permutations whose size is at most 3/4 n. And for each permutation in the set, we'll assign some color, CP, to the edges of the matching that corresponds to that permutation. So here I've just got the same picture as before. These three edges are colored red, and the straight edges are all colored blue. And what you'll notice is that some edges will not get air color. So there's a bunch of edges which are uncolored. I'll call them blank edges sort of from now on. And then some edges will get multiple colors. So everything has a list of colors. The list might be empty. The list could be up to size 3/4 n. But it's important to note that each color forms a matching. So no vertex sees two edges which have the same color, which share a color. Okay. And what we're looking for now is what I'm going to call a rainbow matching. So a matching is rainbow if no color is repeated. And we want to find a perfect rainbow matching. Because remember, perfect matchings correspond to permutations. So for example, in this situation here, we have 3 permutations, which I've represented with the coloring. And in this case, these 5 edges form a perfect matching, and no color is used multiple times. We would be allowed so there are a bunch of black edges which I haven't drawn because I didn't want it to be too crowded. So I only drew the colored edges here. So we would have been allowed to take some edge which has multiple colors on it. That would be fine. But generally, it works out better if we don't do that. So here, this perfect matching corresponds to the permutation 1, 3, 5, 2, 4. And you'll notice that the condition that this is a rainbow matching corresponds precisely to the condition that the covering, that the distance to the set of permutations here is at least n minus 1. So it matches each of these permutations in at most one position. Okay, so is it clear what the goal is, more or less, hopefully?
So you have a perfect rainbow matching, then the covering radius is going to be n-1, and therefore...
Yes, that's right. That's right. That's right. So we want to show that no matter what the starting set of permutations was, provided that it had size at most 3/4 n, we can find this perfect rainbow matching, which will then give us this permutation which witnesses the fact that, yes, the covering radius is at least n minus 1. Okay, so that's the goal. And here's our strategy. So what we're going to do is we're going to take a rainbow matching. We're never going to consider any edge which has multiple colors. We'll completely ignore these edges. Well, not ignore them, but we'll never use them. We want to maximize the number of edges in this matching. And subject to this, we want to maximize the number of blank edges, the number of edges with no color. Okay. What we're going to do when we have something like this, so we're going to consider alternating paths. So these are paths in which every second edge of the path is in our matching M, and at least one of the endpoints is not yet matched. And then to switch on this path, we just mean we add the edges of this path to the matching and remove the edges from the intersection. And you'll see that, that when we do this sort of operation, we will always end up with a new matching, which if we're careful about the paths that we consider, will be somehow an improvement on the previous matching that we had. So we'll assume for contradiction that M is not a perfect matching. And to reach the contradiction, we'll just consider a certain set of alternating paths which will allow us to improve M and therefore contradict our choice of M. Okay, so there's going to be some conditions that we want to impose on the alternating paths that we consider. We want to maintain the property that M doesn't have any edge which has more than one color. So we want to assume for nice alternating paths that, that these paths don't have any edge which has more than one color. We also want to assume that no color appears more than once, because we're going for a rainbow matching in the end. So we don't want to add two edges that have the same color, for example. And we also need to be careful that when we add new edges, we don't use any color that's already being used by the matching. Okay, so these conditions, any path that satisfies these conditions, we'll call a nice path. And we'll look at some more particular restrictions as we go forward.
You also complete the case where you can use a even say no color appears more than one, like no color appears second. I mean, this second.
Yeah, we could clarify and make this more precise. So this is a stronger condition than we would technically need. But we can just, this condition just works, so we'll just take this condition. So just say that on the entire path, no color is repeated. And yeah, things just work a bit nicely if we just do this. Yeah, so we could, for example, add an edge of color red as long as we removed all the edges that had color red from the matching when we did it. So there could be some parity thing that we could try. Okay, so the first type of alternating path that we'll consider are paths of even length. We're going to ask that they start with some vertex which isn't matched yet, and finish with some edge which is matched, but which has some color, at least one color. Well, exactly one color given the restriction. And we're going to only consider these paths if every other edge of this path is blank. So there's no other colors on this path. Okay, so if we find such a path and we switch on this path, so put in the opposite edges back into the matching and take out these edges from the matching, then we will obtain a new matching. And the matching will have the same size, and the matching will still be a rainbow matching because we haven't added any colors to this matching. But we've increased the number of edges which don't have any color because we've replaced this colored edge with this uncolored edge. So this means this would, if we find such a path, this would contradict our choice of M because we chose M to minimize the number of uncolored edges. Okay, so we're going to define these two sets. So let A1 be the set of vertices in V, which are endpoints of blank alternating paths of even length. So these paths starting from some unmatched vertex and continuing on only using blank edges where every second edge is in the matching. Okay, and similarly we define A2 to be the same thing but on the other side of the partition. Okay, so A1 contains only vertices of V because of this even length condition, and A2 contains only vertices from W. But what we notice by considering these type 1 alternating paths is that if we start at some vertex in A1 and we consider any blank edge which starts from A1 and goes anywhere we like, then there is a corresponding vertex which is also in A1. Because otherwise, if this vertex here isn't in A1, then we would find this, then it must be because this edge has some color, and that would correspond to a path of, an alternating path of type 1. Okay. So we have some picture that looks a bit like this. Where whenever we have these edges like this, neither of these two edges can be a colored edge for the matching, or else we would do a switch. So we can add these vertices to the set A1 And similarly, we could add these vertices at E2. And yeah, the important thing to notice is that there's a relationship between the size of this set and the number of blank edges incident to a vertex in this set. So each of these edges should correspond to a different vertex from the set. Does that make sense? Oh, okay. Does anyone have any questions? We're sort of considering things that would look like these paths like this, but then we say that since this edge here isn't allowed to have a color, we know that there are a bunch of edges which have to be blank. Basically, we're looking for a condition which forces some of the edges of this matching to not have any color, so that the number of edges which do have a color is then smaller than we can put some bound on the number of edges of the matching which are allowed to have any color at all. Okay. The second type of alternating path that we'll consider is so paths where the length of the path is now odd. They start and end with vertices which are not yet matched. And at most one edge in this path has a color. And because we've put the nice condition on it, we'll say that this color doesn't yet appear in the matching, and there's only one color on this edge. And we see that if we switch on such a path, then we increase the number of edges of the matching, and we preserve the property that it's a rainbow matching. So this would contradict our choice of M if we find such a path. So the consequence that we get by considering this is that whenever we have a vertex in A1 and a vertex in A2, the edge between these two vertices must either have some color which is already used in M, or have some color which or have at least two colors, because otherwise we would find this type 2 alternating path by sort of combining a blank path with this single edge and another blank path. Okay, so this is the consequence that we find here, is that between this set up here and this set down here, all of the edges have to either contain edges which are already used by the matching, or contain edges, or contain at least two colors, or have at least two colors on them. Okay, and the final type of alternating path that we'll consider is paths, again, of odd length, starting and ending with unmatched vertices. Now we require that one of the edges from the matching part of the path is colored. So we have this path like this, and the central edge has a color. Hopefully it's clear that that's not black, that's purple. And at most two edges not from the matching are colored. So it's these two edges here. Okay. And again, if we find such a path, we would be very happy because we could switch on such a path, and we would increase the number of vertices. But since it's nice, it's a larger rainbow matching. Okay. But what we find is that whenever we have a path of length 3, starting in A1 and ending in A2, whose middle edge is from the matching, if this path is nice, so it doesn't use any edge from the matching, and these have distinct colors and they're only one color each, then we could always extend such a path of length 3 to a nice path of type 3 here, just because just by the definition of this set A1 and this set A2, we can find find a blank alternating path which connects this vertex to an unmatched vertex, and similarly find a blank alternating path which connects this vertex to an unmatched vertex. Whenever we consider some vertex from A1, some edge, some colored edge from the matching, and some vertex from A2, we have the potential to extend to find an alternating path of type 3. So in every case that looks like this, so whenever we consider one colored edge from the matching, one vertex from A1 and one vertex from A3, we know that something has to go wrong. These paths of type 3 shouldn't really exist by the maximality of M. So what could go wrong? So maybe the reason that this path isn't nice is because this color is the same as this color. And then we couldn't switch on some path containing this segment here because we wouldn't have a rainbow matching at the end. But if this is really the only reason that this has gone wrong, then what you'll find is that this sort of obstruction can only occur once for every edge of the matching. Because if the same type of obstruction occurs twice, so we have this red pair of edges and this orange pair of edges, and they're both, only using one color and using colors which are not in the matching, then we can also find a nice alternating path of type 3. So here we could switch one of the red edges and one of the orange edges, and because these were sort of nice otherwise, this path here is a nice path of type 3, and when we switch on this path, we would improve the matching M. Okay, so this means that this type of obstruction only occurs once for each edge of the matching, or once for each colored edge of the matching even. But the number of ways that we can take a vertex from A1 and a vertex from A2 is actually quadratic, because these sets actually have to have, it turns out these sets have to have linear size, which basically follows from the fact that every vertex has at least 1/4 of the edges incident to it with no color. So yeah, what we find is that we can pick some pair of vertices, one from A1 and one from A2, such that whenever we look at these paths of length 3, this sort of obstruction doesn't occur. Okay. So now we're going to define a few terms. So we'll let B of U be the number of blank edges incident to a vertex U. M of U be the number of multicolored edges incident to a vertex U. And let C be the number of colored edges which are used in the matching M. So what we find is that the number of blank edges incident to a vertex is at least the total number of edges, n, minus the total number of colors, so that's 3/4 n, the size of S. But if there are multicolored edges incident to the vertex V, then each of these multicolored edges uses at least 2 of the colors. So actually the number of, the more multicolored edges there are, the more blank edges there have to be in this one-to-one correspondence, at least. So what we find is that the number of blank edges is at least n on 4 plus the number of multicolored edges from this inequality. And similarly, this holds for W as well, for the vertex on the other side of the partition. Okay, so this was the conclusion that we wanted to reach from the paths of type 1 was that the size of the set A1 should be at least the number of blank edges incident to a vertex V plus 1. And the plus 1 is because A1 also contains all of the unmatched vertices. So, so going back to that picture, so here, for every vertex in here, we have a blank path of length 2 leading to this vertex. If we consider some blank edge from this vertex to another vertex in this graph, then we know that any matched edge incident to that vertex has to be a blank matched edge, which then allows us to extend the path so that we find another vertex which is also included in the set. So this gives us this inequality here that the size of the set should be at least the number of blank edges incident to the vertex plus 1, which again is at least a quarter of the vertices, or a quarter of n, sorry, plus the number of matched multicolored edges plus 1. And finally, we find that the total number of colored edges is at most n plus 1 minus the size of A1 minus the size of A2, because no vertex in A1 is included in a colored edge from M, and no vertex in A2 is included in a colored edge of M. So yeah, we have an inequality that looks like this. Here's the picture again. So we're considering, we want to consider paths of length 3 from some vertex V to this vertex W, where the central edge is a colored edge from the matching. Now, for every path that we consider, suppose for contradiction that for every path that we consider either the first edge of this path, so the edge VWJ, or the second edge, or the last edge of the path, VJW, either has multiple colors or has some color which is already used by the matching. Because if both of these edges fail this condition, then we could extend this to some nice alternating path of type 3. These are the only other possible things that could go wrong if we want to find a nice alternating path of length 3, of type 3. But what we also know is that all of the edges from the set A1 to the set A2 also have multiple colors or have some color in M. So this was what we found from considering the type 2 alternating paths. So what this means is that so for every colored edge from the matching, so for all this number C, there either has to be some multicolored edge incident to V, which is connected to C, or some edge incident to this, which has some color which is used by C. And none of these edges are incident to the set A2. So we find some inequality like this, and then essentially we just apply the equalities from the previous page, and we get this contradiction just by combining all the inequalities, essentially. Yeah. So yeah, the conclusion is that actually we're forced to find some type 3 nice alternating path, which then allows us to improve the matching, given assuming that M is not yet a perfect matching. And so the final conclusion is that M is a perfect matching, and therefore we have this result that Fn2 is at least 3/4 M. Yeah, hopefully at least some of the ideas, the general approach made sense. Okay. So I'll finish just by talking about some general bounds on the function fns, so for arbitrary s. So so Cameron and Monless showed that provided s is at most roughly half n, then fns is bounded by e times s factorial times n log n. So our first improvement was this, that so for s at most n minus 2, we have this upper bound now of 3 times s factorial times n minus s log n. So sort of a little bit of an improvement here. And using similar techniques to the Fn2 case, we get this improvement for small values of s, where we have this general bound here, 2 plus square root of 2s minus 2 on 2 times n on 2 as a lower bound for fns in general. Okay. Thank you. Transposition distance. I don't. So people do look at all sorts of metrics on permutations. I don't know if this particular question has been looked at for that particular metric. Yeah, not to my knowledge, but it's quite possible. Yes. Yes, that's right. I don't know. Like, yeah, we get a result which is, which is stronger than what we were looking for. It has these extra properties. Actually, it also, there's a couple of extra properties that we get from this approach. Yeah, I don't know. I don't know if they're of any particular general interest, but yes, we do get extra. We do prove something a bit stronger.
How likely?
Oh, so I. Yeah. So I think most people believe, for example, Ryser's and Brualdi's conjectures. So so these conjectures, I think most people believe. I think I also believe this one, that this maybe is the reason that these two are true somehow, is that we have this property. I'm not sure. It seems it's hard because these questions quickly become computationally infeasible. Like even for like order 10 or like 11, then studying Latin squares of order 10 is sort of it's the computation time for these things So there's an open question of like how many mutually orthogonal Latin squares of order 10 you can find. And people have tried attacking this with computers quite a lot, and it's these things quickly become very difficult to calculate. But generally, people suspect that these statements are true, which is maybe, and generally I would expect that something like this is true. Although yes, it is quite possible. There could be even a counterexample to this of like 15 vertices or something. We really don't know.